Okay, hai, Assalamualaikum semua. Okay, so today hari ni kita sambung dengan another topik, subtopik which is space truss. Okay. So share screen. Okay. Okay, so space truss. Okay, so what is space truss? Okay, a space truss is three-dimensional counterpart of the plane truss. Okay, so this is triangular plane. Okay, triangle plane, but in 3D. Okay. Okay, so in this space truss, okay, it requires 6 bars joined at their ends, okay, to form the edges of tetrahedron, okay. So it has 6 bars here, okay. So you can see this is 1, 2, 3, 4, 5, and 6. 6 bars, okay. And then, okay, so we can see that 2 bars, okay, AD and BD join at D, okay. So this bars AD and BD, okay, they join at D, okay. So they need a third support CD, okay, to keep the triangle ADB from rotating about AB, okay. Okay, next, okay, we see in figure. Okay, so this is what I explained. Okay, so you keep this triangle ABD from rotating at AB. Okay, so they need a third support, which is CD. Okay, this is the support. Okay. Okay, next. Okay, in figure C. Okay, now we refer in figure 14C. Okay, the bars AF, BF, and CF, okay, are attached to the foundation, okay, and therefore its point F in space, okay. So here, where is AF, BF, and CF? AF, okay, and then where is AF, BF, and CF? Okay, so this one, AF, okay, and then we have BF, and then we have CF, okay. So it is fixed at point F, okay. And then we have AH, DH, and CH, okay. AH, DH, and CH. Okay, so this one color AH, DH, and CH, okay. This one they fix at point H, okay. Okay, then this one, okay, the third truss is CG, FG, and HG. CG, FG, and HG. Okay, so CG, FG, and HG, right? Okay, and HG. Okay, so CG, FG, and HG, right? Okay, and HG. Okay, so CG, FG, and HG, right? Okay, and HG. 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 fix at G point. Okay, and then so this structure we call it a space truss. So a space truss is formed. A space truss formed in this way is called simple space truss. So this is an example of simple space truss. Then so now we want to determine either the space truss is stable or not. Or in other terms, statically determinate or not. So because the equilibrium of each joint is specified by three scalar force equations, they are in all 3J such equations. For a space truss with J joints. So this one got how many joints? There are 3 joints. 1, 2, and 3 joints. And then the entire truss is composed of M members. And then there should be 6 unknown support reactions. So and then thus for any space truss, the equation m plus 6j equal to m plus 6 equal to 3j. We say that it is statically determinate. And then if m plus 6 more than 3j, because we can say that it is redundant members. And then if m plus 6 less than 3j, so we call it has deficiency. And then it is unstable. And then so we can use method of joints to satisfy the complete vector equation sigma of f equal to 0. We normally begin the analysis at a joint where at least one known force is there, and not more than 3 unknown forces are present. And then for method of sections, the two vector equations, which is sigma of f equal to 0 and sigma of moment equal to 0, must be satisfied for any section of the truss. Now, for more better understanding, we can see the example here, which is sample problem 4-5. So let's read the question. The space truss consists of the rigid tetrahedron ABCD, anchored by a ball and socket connection at A. And so it prevented from any rotation about X, Y, or Z axis, by the respective links 1, 2, and 3. So, and then we apply load L to joint E. So here's the load L, which is rigidly fixed to the tetrahedron by 3 additional links. Solve for the solve for the forces in members at joint E. So now we have to find the force I don't know, this one got a little bit dark. Okay. Then okay, so my computer got hot, so I just switch on the fan. Okay. Okay, and then okay, so now what we have to do is we have to find so let's find out the keyword, main keyword here. So the keyword here is, okay, we have to find forces in members at joint E. Okay, and then we have constraint at ball and socket connection at A, and then we have respective links 1, 2, 3. Okay, so okay, so now okay, note that we note that okay, the truss is supported with 6 properly placed constraints. Okay, so this one is ball and socket joint, so it will have 3 forces. Okay, and this like this, and then this one is like this, like this. So there are 6 6 what you call it, 6 constraint. Okay, 6 properly placed constraint. Okay, 3 at A and links 1, 2, 3. So 3 here is this one. Okay, 3, 1, 2, 3, 4, 5, 6. Okay, so this is the 6 constraint. Okay, and then members we have 9. Okay, so now let's identify where is the members. 1, okay, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there are 9 members. Okay, and then we have how many joints? Okay, we have maybe this one, I guess. 1, 2, 3, 4, 5. Okay, so there are 5 joints. Okay, so we have to check either this is stable or not, statically determinate or not. Okay, so the equation is m plus 6 equal to 3j. Okay, so now we have m equal to 9. Then j is we have 5 joint. Okay, so 9 plus 6 is equal to 15. So it is satisfied. Okay. Okay, so it can provide non-collapsible structure, and then the equation is satisfied. Okay, now where should we begin? Okay, so we start with a joint on which at least one known force is there. Okay, and not more than 3 unknown force. Okay, so basically we just choose joint E. Okay, because we have one known force, which is L. Okay. Okay, so okay. Okay, so I just put some extra note here. Okay, choose joint E. Okay, as there is one known force. Okay, and then please remember when it is in 3D, okay, please calculate in vector form. Okay, which is I, J, and K. Okay. So now we are going for section joint E. Okay. So now we are going to calculate the vector unit. Okay. So vector unit is what? Vector divided by distance. Okay. So now we calculate FEB first. Okay. So for FEB, okay, so where is FEB? First we just assume it is going outward. Okay, so we just assume outward. So this is FEB. This is FEC, and this is FED. Okay, so FEB. So this is FEB, right? So we have in this way. Okay, and then we have this way. So this is SSZ. So -3I. Okay, so always remember this is positive, this is positive, and Y should be this is positive. Okay, so FEB we have -3I. How come here is 4? Yeah. So this is 3, -3 G. Okay, because it is in y-axis. Okay, in line with y-axis but heading to the left. Okay, this one y positive is heading to the right. Okay, so FEB we have -3I, -3J. Okay, so the total distance is 3 squared plus 3 squared, square root everything. Okay, and then we just simplify. Okay, so this is let's say this is I, J, so just put 3 out there, and then this one we have 18, right? Okay, so 3 -I -J 9 2. So this one is okay, so we have square root 2 square root 9. Okay, so 3 2, so we can cancel out. So this is what left. Okay, now we calculate for FEC. Okay, FEC. Okay, we have, okay, this is one going here and then here. Okay, so this one is -4 Z or for K. Okay, then this one is -3I. Okay, for FEC is equal to -3I minus 4k. Okay, and then 3 squared plus 4 squared, negative 3 pi minus 4k 5. Okay, don't forget we have the value, the vector value, the value. Okay, so we just f e b f e c. Okay, next is f e d. Okay, so f e d, where is it? So it's just going downward. No, oh, this one. Okay, so the same, negative 4k. Okay, and then this one is negative 3j. Okay, so FED equal to negative 3j minus 4k. So 3 squared plus 4 squared equal to 25. Okay, negative 3j minus 4k over 5. And the value. Okay, so we take sigma f equal to 0. F equal to 0. So A plus F E B plus F E C plus F E D is equal to 0. Okay, now we do this in vector form. Okay, so L is heading in I direction, negative. Okay, so L will be negative Li. Li. Okay, okay, write down again. Okay, negative Li plus FEB is negative I, negative j over square root 2, and then the value b plus negative 3i minus 4k. Okay, and over 5 FEC plus negative 3j minus 4k over 5 FED equal to 0. Okay, so now we do for I first. Okay, I. Okay, maybe I should say for I, okay, we have negative Li minus I over 2 FEB minus 3I over 5 FEC equal to 0. Okay, so we just take the numbers only. Okay, we exclude the I, so we have negative L minus 1 over square root 2 FEB, okay, and then minus 3 over 5 FEC equal to 0. Now we have FEB equal to square root 2 negative L negative 3 over 5 FEC. Okay, so we say this as equation 1. Okay, okay, now we do for J. For J, we have okay, wait, I think, okay, for J, we have negative J over square root 2 FEB minus 3J over 5 FED equal to 0. So we take out the J. So what left is negative 1 over square root 2 FEB minus 3 over 5 FED, okay, equal to 0. And then we have negative, okay, so that's it. So this is we take as equation 2. Okay, now we put equation 1 into equation 2. Okay, 1 into 2. So FEC is equal to 5 over 3 negative L plus over 5 FED. Okay, d5 over 3 plus FED. So this is equation 3. Okay, now for K, we have negative 4 over 5 K FEC minus 4 over 5 FED equal to 0. Okay, and then so this one we just take out the K, so we have negative 4 over 5 FEC minus 4 over 5 FED equal to 0. So we can see that FEC plus FED equal to 0. So this is equation number 4. Okay, so now you put equation 3 into equation 4. Okay, so 35 over 3L plus FED plus FED equal to 0. So 2 FED equal to 5 over 3L equal to 5 over 6L. Wait. Okay. Okay, so since FED is for 5 plus L, okay, so FEC will be from this one, okay? C will be negative 5 over 6L. Okay, now from equation 2, this one is it? OP. Okay, so from equation 2, okay, we just input the FED, okay, so 31/2 FEB minus 3/5 FED is 5/6L. Okay, so since cancel 1 and then 2. So -1 square root 2 FEB minus 1/2L equal to 0. Okay, and then oops, sorry, forgot the FEB. FEB okay, equal to 1/2L. Okay, so this one FEB equal to negative t square root 2. This one is 1 2L. Okay, so you can cancel out. So FEB is equal to negative 1/2L. Okay, so let's see, we have find out the force of FEB, FEC, and also FED. Okay, FEC, FED, and where is FED? Or EB. Okay, EB here, EC here, and ED here. Okay, so that's all. So okay, so that's all. Thank you very much. Okay.